All right, hey guys, my name is Akshay. Today I'll be presenting my work on resource utilization as a metric for machine learning. Before we start, I'll quickly cover some of the details about myself. My name is Akshay Bhaga. I'm currently working in the field of machine learning and big data for the past 3 years, and this is one of the projects. This is one of the topics that I'm really passionate about, mostly because uh, in a country like India, I feel that resources are limited, and therefore it's very important that we use these resources carefully. And therefore, I just want to lay the emphasis on resource utilization aspect when we're working on learning models. Okay, so before further ado, I'll quickly start the presentation. So it's going to be about 60 slides, and I'm going to cover them in around 45 minutes. I'm recording the session beforehand because it's a virtual conference, and feel free to reach out to me with any questions. All right, so let's get started. Before we start, actually, I just want to say thank you to Confer for organizing the event. The thing because of the pandemic, people have less content at hand and they want to learn a lot of new technologies. So I think Conf is definitely going to be very helpful when it comes to different people coming together and collaborating, and also teaching new stuff to in the field of AI, cloud, as well as machine learning. All right, so we'll start with some of the very basic concepts. And before that, this is an important link. So if you want to have a look at the slides, or if you want to have a look at the code for the session, go to bit.ly/confer-20, and you'll be transported to my GitHub page for Confer 2020, and you will find all the relevant links. You can even ask me questions on GitHub itself, and I'll be more than happy to answer them. And towards the lower right, you will find my website, akshaybhaga.com, where you can reach out to me. All right, so what is machine learning? I'll just quickly cover the basics of machine learning. So we have an ordinary system. So any system that works currently without learning capabilities is considered to be an ordinary system. So with the help of AI, AI is basically giving intelligence to a system, and this can be done in multiple ways. So machine learning is one of the ways, and machine learning basically means that you are feeding data to the system. Okay, so with the help of AI, we want to give intelligence, and how will we do it? We'll do it via machine learning, that is by giving data, and over a period of time, our model will start to learn, it will start to predict, and it will start to improve itself as well as the insights. So this is how a basic machine learning architecture looks like. And we'll start with the very basic concepts. So we'll start with EMNIST, and I assume that you guys must have heard of EMNIST. It's one of the basic data sets that we use while working with computer vision technology, while starting with computer vision. So we'll quickly go through the basics of it. So for EMNIST as well, this is how our data set looks like. So we just going to call a function called as show data, which will show us different digits. So this is how the data set looks like. So given the image, we have 28 by 28 size of the image, and we'll have the label which corresponds to a digit. So in the image, you can see that this image that is displayed is of the letter is of the number 3, and similarly you will find the label is also 3. So we want to categorize different digits based on their digital value or digit value. Okay, now let's go into some more details. So let's say if I print out the shape of it, shape basically means the pixel values. I'll know that the image contains 28 pixels in height and 28 pixels in width. Now, if I do a print of it, so you will find the scatter diagram, and this is actually all the pixel intensities. So the pixel intensities vary from 0 up until 255. So we'll have the minimum value 0 and the maximum value 255, which corresponds to the pixel value of each pixel value of each product, of each pixel. All right. So now one thing that we notice here is that the spread of the data is quite sparse, which means that the lower value is 0 while the upper value is very high. It's around 255, and you have a very skewed data set, which means that the spread is not even. Now we have a very simple concept of normalization, which all of us might have studied in class 10th or 12th. I studied in class 10th when I was studying basics of statistics, and normalization means that you control the spread of the data. Okay, so what I'll do is I want to practice normalization on this data set. So in this case, I will divide the entire data set by the maximum pixel density, which is 255. And once this happens, although the shape is the same, so we have 28 by 28 shape and size. However, what we notice is that the lower value is 0 and the maximum value is 1. Okay, so earlier our data set was from 0 to 255. Now it has come to 0 to 1. Okay, so we have contained the spread of the data. Now the data is not very skewed. All the data set will lie between the value of 0 and 1. Similarly, if we want to have a mean of 0 and the minimum value -1 and maximum value +1, we have something like this. So what I'm trying to do is I'm trying to divide each pixel value by 127.5 and I'm subtracting -1 from it. Now what happens in this case is that I'll have the minimum value -1, I'll have the maximum value of +1, and you can also find that the mean of the spread is 0. And this actually helps in convergence. So we have two kinds of normalization. This is a zero mean normalization in which the mean of the data set comes out to be 0. And we'll see how it affects our training. So I do some of the simple calculations right now. I'm trying to see the number of training examples. I'm trying to see the number of test examples, and similarly, and we'll move forward from here. Okay. So now, if we look at the model, our model is pretty basic. We are not even using any CNNs. We are using simple feed-forward networks, and we'll look at the model in detail. But the important point is that we are using simple models, so we are not working with CNNs. Now, if I do a model.fit on the normal data set, that is the data set which had the spread from 0 to 255, what we'll notice is, first of all, we notice this is the model graph. You can find different parameters here, but this is not really important for us right now. What is important is the total number of parameters. Okay, and this is around 468,000. Now, if we call the model.fit function on this, you can see that each step takes around 68 microseconds, which is quite good for us. But the point of a problem is that even after 2 epochs, the accuracy is around 26% and the loss is 11, which means that our model learning, but it is not learning at a very high rate. So if I call the same function, if I call model.fit on a normal on normalized data set, what I'll find is that although it's taking similar time, it's taking around 70 microseconds per step, which is similar to what we saw earlier, but the accuracy is actually increased to 93%. So what this means is, with the same data set, we had the capability of increasing our accuracy 4 times, which means that we have to train our model for a lesser number of epochs, and therefore we are saving resources. Now, in the next case, if we want to look at the normalized data, which had the mean of 0, what we'll find is that this also takes similar time and the accuracy is similar. Therefore, what you notice is that using a simple concept, a simple mathematical concept of normalization, which we studied back in class 12th, which is one of the most basic concepts of statistics, we are able to identify the problem in a model, and we are also able to fix the problem without actually changing the architecture. So this actually helps us a lot when we're working with a different, very high, a very, you can say, a lot of data in real time. And this normalization techniques helps us a lot because you're going to optimize much more quicker, and then therefore you're saving resources. All right, so we'll quickly move to the next concept right now. Uh, all right, so before moving to the next concept, I just wanted to show the graph for the learning. So if you see this on the left, you will see the graph for working on unnormalized data set, and you can see that the accuracy is actually decreasing over time, which means that our model is not learning. On the right, we have the graph for the normalized data set, and therefore you can see that the accuracy is around 92%, and it's going steadily upwards, and that's actually a good sign. Now we'll discuss a couple of other concepts in details. We'll talk about optimizers. So optimizers we'll talk in detail, but the important aspect is we are using the same model from a previous question or from a previous use case. What I'm trying to do is that I've tried to pass optimizer as a variable in the function itself, and I'm just calling it when I'm compiling the model. So I can change it at runtime. I can try out different optimizers, and each optimizer helps me optimize the model in a certain way. And we have different optimizers, and every optimizer has its own good qualities, and some of them have some bad qualities as well. So we'll try to look at that. Doesn't mean that one optimizer is better than the other one. It means that whichever suits the use case, you can go ahead and use that. Similarly, if we look at the model definition again, the number of trainable parameters remain the same. So we have something called a stochastic gradient descent, or SGD. SGDs are mostly used if you want to work on a data set and you want to learn quickly. So if you want to take quick steps towards the minima or towards convergence, you can go for SGD. So what I'm trying to do is I'm trying to call SGD, and the important point that I notice here is that even though the accuracy is not very high, so this is just calling for, I think, one epoch. So even though the accuracy is not high, the time taken is actually less. So earlier we saw that, and we're working with the same data set. So we're working with EMNIST. So earlier we saw that a model took around 70 microseconds per step. Right now it's around taking around 59 microseconds per step, which means that it is pretty fast. So if you're working with real-time applications, if you're working with some real-time data and you don't want to have a lot of lag in the system, SGD is a good option for you. And we have something called as RMS prop, which is an optimizer which takes into account uh, the difference from your point to the minima. Therefore, because it takes into account different aspects, uh, the accuracy is high, but then the time taken is slightly higher. So in some cases, the time taken, doesn't really matter if you're working with static data or if you know that the lag is going to be there in the pipeline at some point. Therefore, you can go with RMS prop. But if you're working with a very high rate of incoming data, you can go for SGDs. Now we'll talk about activations. Okay, so while talking about activations, I'll quickly show you the model once again. So we are using a simple model. We are using the CNNs. I'm passing on activations as an input parameter, and I'm simply causing activation on any layer that I want to. And activation, the concept is basically I want to provide a non-linearity to the data set. So I don't want my model to learn only linear operations or only linear information. I wanted to learn maybe non-linear relationship between different features. And again, the model definition remains the same. So we have the same model. Nothing is changing in this. Now we have something called a sigmoid. Sigmoid provides a non-linearity by changing our data and keeping the range between -1 to +1. So if your data has a very high value, let's say 1000 or 2000, it's going to directly converge it or directly turn it down to the value 1. And if it has a really high negative value, it's going to make it tend towards -1. And this is basically providing non-linearity towards each feature, and it performs really well. So if you see that in this case, you're working with the same data set once again. The loss is around 0.68, accuracy is around 80%. And we have also something called as ReLU, or rectified linear units, which became quite popular in the recent times. And the important aspect about ReLU is that it clips the gradient, so you don't have the problem of exploding gradients in your code. So if you look at the code for ReLU, uh, for the same time or for the same number of epochs, the accuracy is considerably higher. So if you're working with a data set which you think that it can have some gradient exploding or gradient vanishing problems, you can simply use ReLU as your activation, and it's going to perform really well. Now we have a concept called as learning rate decay. The concept of learning rate decay is basically you want to make sure that when you're going towards minima, or when you're converging your model, you don't want to overshoot it. You don't want to overtrain your model and end up going away from the minima. Therefore, what we do is when we're uh, starting to learn, we can learn quickly. We can learn a lot of information at one point. But as we go towards the minima, or uh, as we go towards a point where the error is is the lowest, we want to make sure that we stop at that point and not keep on learning after that. So the concept of learning and decay comes, helps us in this use case. So what we do is basically we can have a callback function, and callbacks are basically at the end of every epoch or at the end of every training session. You can call this function or call this callback, which will say that on the batch end also. That's if I'm training on a batch size of 64, 64 samples. On every batch end, what I want to do is I want to divide my learning rate by the number of iterations. Okay, so let's say if I'm on the first iteration, it's going to be fine. If I'm on a 100th iteration, it's going to divide my learning rate by 100. So it means that you are going to keep on decreasing the learning rate, so that as you go towards the minima, you stop at that. You don't want to keep on learning even after you are at minima. So if you see that in the callback, so I've called the model.fit function. In the callbacks, I have declared the callback as Adam learning rate tracker. And if I train this, what's going to happen is that my learning rate for the 100 iteration is this much. And as you go forward, at the 400, it has gone down to 0.000003. And at the 1000 iteration, the learning rate has gone down to a considerable value, and the accuracy is around 85%, which means that, and as you can see, that the accuracy is actually increasing at every step, which means that we're learning, and at the same time, we're also making sure that we are not overshooting. Okay, so now we have come to EMNIST. We actually saw the couple of examples for EMNIST, which is for digital recognition. EMNIST is for alphabets. And let's see the video. So this is, I think, one of the initial works that I was working on. It was, I think, only for my own personal experience. So right now you can see that I'm actually drawing the alphabets on screen using computer vision. So I have integrated computer vision with machine learning, and you can see that I have three models in place. So I have a simple logistic regression model. It's performing well. I have a shallow network, which is also okay. And I have a deep network, which has multiple layers in between. It has multiple nodes in between. And as you can see, in most of the cases, my deep network will work really well, because my deep network can actually get some influences from the layers in between. So if you're working with deep networks, and your deep networks might work really well if you have it well configured. But yeah, there's no clear guarantee, but this has been the case, at least with me. So you can give this a try as well. Now we move forward. We'll see at one of the other projects that I did. It's called as DigiEncoder. Uh, so basically, what I do is I do my machine learning model to draw these digits from their own memory. So right now I have three models. I have a Llama network, I have a D network, and I have a CNN network, which CNN works really well with images, and we're going to see that in a couple of slides. What I've done is that I have trained my model on all these digits, and I have told them that you just keep an embedding of it, and as soon as you see the same image or see the same digit, just draw that digit from your own memory. So right now, what they're going to do is that they're going to draw the digits and from their own memory. And similarly, in this case, they're going to draw the digit 0. So in most cases, CNN works pretty well because CNN works really well with images because it has different filters, and each filter can actually help you to understand one part of the image. All right, so let's move ahead. Let's come to CIFAR 10. So this is one of the data sets. The important aspect of this data is that the architecture is pretty interesting on this. Okay, so if we talk about the architecture, so the image size is now we have moved from black and white images to colored images. So now you can see that my dataset looks like a colored image of size 32 by 32, and it has certain labels. So it has around 10 labels. I assume that on the image on the right that you see is of the image of a frog. Although I'm not able to identify it because it is very distorted, it does not have enough information. But that's fine. I just want to test it out. Okay, yeah. So this is a color image because it has 3 channels. So this particular sub use case, we are going to talk about network architectures and different architectures and how they can help us achieve good accuracy, and at the same time, we also want to make sure that our resources are as minimum as possible. So we have an FC architecture or a fully connected architecture. So this is the same architecture that we have been using from the past use cases. And if I train this on the image, first of all, you can see that the total number of parameters are around 3 million. It's fine. We are not worried about that at this point. But if I train it, you can see that the accuracy actually remains the same, which means that my model is not learning anything. And if you look at it logically, because we had 10 images, every time we make a prediction, because this prediction will be 1 out of 10, we anyway had a accuracy of 10% even at the starting, even if we did not learn anything. Right now, it's also doing the same thing, I feel, because accuracy is around 10% and does not really help us into solving our purpose. Okay, and it's also taking a lot of time, taking 127 microseconds per step, but that's fine because we are working with a lot of data. And as you can see with all of this graph, the accuracy is actually constant, or you can even say that it is that the model is not learning anything at this point, and that's quite a waste of time because we are using resources for training it, and after training we realize that our model is not even learning anything in the first place. So for this, we are going to use a CNN network or a Conv network. As already explained, CNN works pretty well with images because each filter can help you identify a particular shape or a particular color from the entire image, and it really helps us. So as you can see, this is our model. We have conv layers, we have certain max pooling layers. We're not going to talk about them in details, but basically you can understand that each of these layers is going to help the model learn a lot of features, and that's going to help it identify which image does it belong to, or which class does the image belong to. Okay, so yeah, so we have a conv network. Okay, So now if we look at the image or if we look at the model, the total number of parameters are less. Okay. And at the same time, if you are training it, the accuracy is around 40%. And the time taken is also less. So the time taken is around 99 microseconds per step. So we are saving time, we are reducing the number of parameters. At the same time, our accuracy has increased. So this is actually a good practice or good starting point for us if you want to play around with the architecture, just to make sure that we're learning something at the end of the day and we're not wasting resources. Similarly, it takes less time, and the graph that you see also helps us identify that our model is actually learning. Now we'll talk about one of the use cases or one of the research papers that I researched on. So it's called as Autopilot NVIDIA. That the actual name of the paper is end-to-end learning for self-driving cars, and it was, I think, released by NVIDIA while they were working on autopilot or autonomous driving. So autonomous vehicles consider autonomous driving. They contain a lot of different modules. One of the modules is called as behavior cloning. Behavior cloning means that given the image of the road, you want to identify the steering, the angle of the steering wheel. Okay, so this model, this paper talked about that. So if we look at the research paper, it also contained some data set. So the data set was around 2.9 GB zipped. And if I uncompress it, it's going to be much more than that. Okay. And let's look at the image. So this is how the image looked like. And similarly, this is the next image. So you have the road of the image of the road. And at the same time, you will also have a steering angle attached to it. Okay, and at the end of the day, what you want to do is, given a set of images, you want to make sure that the steering angle remains actually, and I mean the steering angle is good, or maybe which means that you are actually on the road while you are using this model. So this is the structure or the model structure that was given in the paper itself. Therefore, it's called as paper model. And if you look at this in detail, what we notice is that it actually has a number of parameters for 132,000, which is quite okay. And the total number of pixels per image is 66 by 200 by 3, which comes out to be around 40,000 pixels per image. And this is a good starting point for us. Now, what I want to talk about is this. So if I load the entire data set into my RAM, so I'm just resizing the image 200 by 200. If I'm loading it in the RAM, the RAM usage comes out to be around 8.7 GB, and this is okay if you have a very good very good laptop. But while I was working on this problem, I did not have such a good laptop. So what I did, or what you could also do in this use case, is that you want to save resources. You want to save your RAM space. You want to save your VRAM. So what we do is we can have a concept called scaling. Basically, what you do is you resize the entire image to a smaller value. Okay, and in this case, the RAM has come down to around 1.1 GB, which is pretty interesting. Now, if you work on this model, if you work on 50 by 50 by 3 image, the number of parameters remain the same. That's okay. And but the total number of pixels per image has decreased, which means that our input has actually lost some of its information, because earlier we were working with 40,000 pixels per image. Now we're working with 7,500 pixels per image, which means that we're losing information. But that's okay. Machine learning is all about getting this information or predicting this information from your experience. Now, what you can do is, if I train this model, uh, what I see is that it's still learning. So the loss is around 0.14, and the number of steps that are taken is around 356 microseconds per step. And you can see the loss is going down, which means that our model is learning. So our model performs really well right now. Now, We can even go ahead one step. So what we can do is we can have some filtering in place. Filtering basically means that you want to filter out the noise from the whole image. And because I was working on colored images, I thought that I have something which helps me understand how the image of the road is different from its its boundaries. So I had something called as HSV format. HSV is called and the full form of HSV is hue saturated value, which means that it's kind of like black and white itself. Although the difference is that uh, the main difference is that it has different shades, or it has different shadows for different areas. So what I knew is that the road will be much better lit as compared to, or the road will be much darker as compared to other surroundings. So I went with my hunch. I thought that this is going to work really well. And what happened is this is the image. So right now I have converted the entire image to HSV format, and you can see that road has a clear demarcation. And in this image as well, you can see that the road has a clear demarcation. So if we load the entire filtered image into a RAM, the RAM usage has now come down to around 757 MB. So it started at around 9 GBs, then it came to around 1.2 GB. Now it has come to around 750 MB, which is quite good for us. But because of lost information, to make sure that our model performs well. So we have a new model in place. And the point that I want you to notice here is that we are only working with 30,000 parameters. So from 130,000, we have come down to 30,000. So we have improved our research paper. And the total number of pixels per image has also decreased. Okay. And this is a good point. And if you are training this model, it's going to perform really well. It is actually learning quite a lot. Okay, and you can see that the loss is going down, which means our model is learning. And the number of time taken is also less because we have removed excess noise from our image. And you can see this graph. The graph is going down, which means that our loss is decreasing. Now the third technique that we could use is fit.generator. Yeah, so if you use fit generator, what we can do is we can directly load images at runtime. So we don't have to keep all the images in RAM. So what we do is we call a function generator from path. We define it. What we do is at runtime, we just call the images that we want, and we do a resize of it. This is just one of the functions that I implemented, and I resize it to 200 by 200. So now we are working with this model. The model is pretty huge, as you can see. Total number of parameters around 10 million. That's okay. And the number of pixels per image is 120,000. Now this means that we have a lot of information in the image, and if you train this, you're going to perform it. So if you look at this particular graph, what you can see is that at the end of the fifth epoch, the loss has actually decreased exponentially. But the RAM usage is around 12 GBs. And that's okay because I was working on, I think, cloud. I was working on Google Colab. Therefore, I had this amount of this freedom of resources. But I would have preferred the last version that we saw about filtering, because we actually saved a lot of resources and we were uh, improving a research paper. And yeah, and one thing to notice is that it takes a lot of time. So earlier we were working with, I think we were working with around 100 microseconds per step. Now it's taking around 2 seconds per step because it has to process so much information. It takes a lot of time. But now the graph that you see that the loss has actually decreased exponentially and performs really well. So let's look at an example. So this is the model that I work and this is the model from filtering itself. What you see here is that it works pretty well, but does not work well with with a lot of noise. And this model is going to work really well when it comes to long roads or roads which have less disturbance. So right now, because it is a highway, I feel it does not have the road does not have a lot of pedestrians. It does not have a lot of noise. The model is performing really well, and my steering angle is also stable. So right now it feels stable. I think if you go ahead, it's going to take a right turn as well. Yeah. So you can see that the model is performing well when it comes to uh, uh, when there is less noise. So yeah, so this is one of the key aspects that I saw. But this is actually a good starting point for any developer. So we'll move on from the slide. Now I'll quickly talk about Indian Sign Language Recognition, or ISLA. Uh, all right, so now we'll talk about ISLA, or Indian Sign Language Recognition. Before that, before going on to this topic, I just want to have a quick recap of what all we did. So we looked at a very simple technique as normalization, which is a very basic mathematical technique, and we were able to use that and increase our accuracy by around 4 times, which is a good point. Second, we looked at a couple of optimizers and activation functions that we could use and how to play around with them. Then we also looked at how to optimize a network architecture to save resources. So we are working with some normal models, and then we also use a CNN model. And then we worked on a research paper called as Autopilot, where we improved a research paper by actually using a lot of filters as well as scaling, and we were able to improve the RAM usage of that model. Now we are talking about Indian Sign Language Recognition, and this is one of the projects that I'm working on currently, and it's pretty close to me. So before we go ahead, I'm just going to give you a small introduction about this. So we're talking about the problem statement. The problem statement is around 40 million people in India are suffering from inequipment. And within 80 kilometers, that's the distance between where I work and where my family lives. And in both the cases, in both cities, sign language is different. Not entirely different, but some words are different, or there are some subtle changes. Now, what an ideal solution should look like? An ideal solution should be to standardize ISL. So we want to make sure that ISL or ISLA or Indian Sign Language should remain same even if I travel from North India to South India. I also want to make sure that I leverage AI so as to predict these minute changes. So if there are any basic changes, I should have a model that can help me identify these gaps and bridge them. At the same time, all the points that I have mentioned before the slides, I'm going to use that, and I'm going to make sure that my resources are less because I already mentioned in India, resources are hard to access. They want to make sure that we keep the resources to bare minimum so that we have good scalability. So this is my experience. I went to a for a couple of months, and these are some tools from which help me understand. So this is the preparation part. Feel free to have a look at that. It's present on my YouTube channel, so you can have a look at the entire 6-minute video about how these kids help me, and I'm really grateful to them. So after this, I realized is for sign language, I'm going to have two information in hand. I have to have the hand gestures, of course, because sign language is all about talking through hand gestures. At the same time, I also want to make sure that I'm capturing the facial expressions and facial key points. So and at the same time, I also want to make sure that my resources are less. So I couldn't work on the entire image. I have to work on part of images. I and this filters were able to filter out just my hand gestures and my facial expressions. Okay, so these are different signs, different gestures for different phrases or different categories, as you can see. And I was able to implement this type. You can all my model or all the input models able to equalize and my expression points and you can see the categorize and with a few uh, and I'm lucky enough actually got a chance to present my work in Google headquarters and present my work there as well. So if I have looked at this 50 around I think 7.5, and so yeah, so this is pretty interesting. So this was it about the entire work that I've done, and how resources, keeping the resources less is one of the key aspects at this point. So also also feel free to reach out to me with any questions that you have regarding this topic or machine learning in general or computer science in general, because I feel that you know answering questions or just having an understanding of how this works are very gives you a very good advantage. Feel free to share your feedback with me. You can go to my website, which is at the bottom, akshayvaru.com, where you can give your insights about how you felt about the whole presentation, what could I have improved, what did you like about the presentation, and what if you want if you want me to add any points or if you want me to add any resources, feel free to do that. I will be more than happy to address all of these problems or all of these discussions. So this has been it from my side. My name is Akshay Bhadur. You can find me on akshayvaru.com. At the same time, you can find the content at bit.ly/confer-20. So feel free to do that. And I'm hopefully I'll see you next time. Take care. Have a great one.